In a previous video, I talked about two of the experiments that led to the discovery of the quantum theory, which are the black body radiation and then the photoelectric effect. And in this video, I'm going to extend this through the Bohr model, which is the third experiment that I'm going to talk about. And before we talk about the Bohr model, I want to first talk about some terminology that we're going to be using when talking about the Bohr model, starting with spectrum. So spectrum is produced when a radiation or a source of light from a polychromatic. So the word polychromatic here, poly is many, okay? And the word polychromatic really means contains different wavelength. Okay, so contains different wavelengths of light. And it's produced when this source of light that contains different wavelength is separated into its individual components of wavelength. And with that being said, the spectrum can be either a continuous spectrum, in which you have all the wavelength of visible light. Okay, so specifically we're talking about visible light, like white light that comes from our bulb. Or you can have something like sunlight. Sunlight has also a continuous spectrum passing through a prism to give all the range of the colors in visible light, like you can see here in the white light spectrum, okay? Or you can have a line spectrum. A line spectrum is only showing very specific wavelength, and some elements have very discrete line spectrum. For example, you can see helium. Helium has different line spectrum from something like barium, which is pretty cool. Now let's move on to the Bohr model. So the Bohr model is specifically designed for the hydrogen atom, is built off of the hydrogen atom. And Bohr proposed an explanation for the line spectrum. So this is the line spectrum specifically for, so let's line spectrum for hydrogen atom, okay? And since a hydrogen atom contains only one electron, so Bohr proposed that the electron in the hydrogen atom moves in circular orbits. So be careful, it's orbits, not orbitals, okay? Because orbitals are different, and we're going to talk about them later in this chapter. So it moves around, okay, the nucleus in orbits, all right? And these orbits are referred to as energy levels, all right, with specific energies. So for example, you have something like N1, N1 you can see is closest to the nucleus, and then a higher energy level is 2 and 3 till infinity. So there are infinite number of orbits. And an electron must occupy one of these orbits. Now, electrons cannot be between the space of the orbits. Okay, so it must be located in one of these orbits. Now, again, an electron may move from one orbit to the other. Okay, so you can go from a lower to a higher energy orbit by absorbing energy, or it can move from, sorry, not energy, photon of light. So, or it can move from a higher energy orbit to a lower energy orbit by emitting a photon. Sorry, it's not energy. And if the electron chooses to stay in the same orbit, there is no energy exchanged at all. Now, the Bohr model of the hydrogen atom, let's talk about how does it relate to the emission spectrum and the line spectrum of the hydrogen. Now, we agreed that the lowest energy which is n equal 1, closest to the nucleus, we can call this the ground state. Okay, so it's grounded, lowest energy. Now, any energy level above 1, so n equals 2 or higher, right, is a higher energy. So an electron can move from n equals 1 to 2, 3, or 4 till infinity by absorbing a photon, and we can say it is in an excited state. Okay? Now, and it goes to the excited state by absorbing a photon. Now, when the electron goes back to a lower energy, so it goes from the excited state to a lower energy level, it emits the photon, right? And through the emission of a photon, now you can see right here, because see, it's going back to the ground state. And when it, depending on the energy level, so if it goes here, for example, from 5 to 1, or from, this is 3 to 1, or from 2 to 1, it actually emits a photon, and this photon has a specific wavelength, right, that corresponds to different lines or different colors of lines in the emission spectra, which is very cool. Now, how can we determine the energy of an electron in each orbit? So, and right here, you are going to use this equation right here, which is the Rydberg equation. This is the 1-point form of the Rydberg equation. By the way, this is given to you on your formula sheet. You do not need to memorize it. So this is on formula sheet, on recitation or exam, right? And right here we have, this is the Rydberg constant. So E is the energy of the photon, equals to negative 2.178 times 10 to the negative 18 joules. And this is the Rydberg constant times Z square, which is the atomic number of the element. And of course, because we are dealing with the hydrogen atom, it's just 1, divided by n square. N square corresponds to the energy level. So specifically for a hydrogen atom, we can use this form of the 1-point form of the Rydberg equation. Now, note, this is again something very important that we should take note of, that as the electron is an orbit close to the nucleus, we assign a negative value for the energy of the electron that orbit, because it is stable, or it's in the lowest form of its energy value. And note that as the electron moves further away from the nucleus, it becomes a less negative value, and we can define the energy of an electron that completely escapes the nucleus as a 0. Okay? Now, I want to also discuss the energy levels right here and the differences between them. So, as the difference in energy, so as we move from N1 to something like N2, right, the difference in energy is quite large. But as we move on to higher energy levels, note that the difference between each energy level becomes smaller and smaller. So note here the difference between N1 and N2, and then N2 and N3, it's smaller. N3 and N4 is even smaller, and so on and so forth. Now, how can we determine the change in energy, right? So this is the change in energy when an electron will transition from one energy level to the other. So in this case, we're going to utilize the 2-point form equation of the Rydberg equation. So the difference in energy will be the Rydberg constant times 1 over the final energy state squared minus 1 over the initial energy squared. And I want to make here a point again, bringing in the line spectrum of the hydrogen atom. And this line spectrum is specifically called Balmer series. It's a scientist who discovered and actually did a mathematical interpretation of the hydrogen spectrum, and now relate this to the wavelength and energy and everything. So again, note that if I use the 2-point form of the Rydberg equation to calculate the difference between N2, let me highlight this, N equals 2 and N equals 3, right? Or let me actually use a color that's corresponding to. So N equals 2 and N equals 3. Note that because these are relatively close to each other, right? The energy difference between them is not going to be as larger or as more negative as the energy difference between N5 to N2, or sorry, N4 to N2, and then N5 to N2. So how does this again relate to our, because we see here energy is again related to the wavelength. So previously we said that energy is inversely proportional to wavelength. So the larger, so we can say that the larger transition, or the larger difference in energy, means that I have a lower wavelength. This is why we can see that the red right here is at a longer wavelength, because the difference between N3 and N2 is relatively smaller than the difference between N4, which appears at a shorter wavelength. And then we have here finally the violet transition right here, which is 5 to 2. Now let's check our understanding, and I'm going to do one conceptual question, and then on the next slide I'm going to show you how to utilize the Rydberg equation, the 2-point form of the Rydberg equation. Now I want us to think about this, and without performing any calculation, which of the following transitions does the light emitted have the smallest wavelength? So 2 things to note. So emission right here means that it's going from a higher energy or higher N to a, or excited state, to a lower energy level. Okay, so this is the first thing, because absorption, on the other hand, so absorption is going to be lower N, I wrote M, lower N to a higher N. Okay, so we're looking for higher to lower, all right? And then the smallest wavelength corresponds to the largest difference between energy levels. Okay, so let's look right here. So first of all, let's go through a process of elimination. So for the first choice right here, this is emission. Well, sorry, this is absorption. So I can get rid of, because it's going from lower to higher, so I can eliminate A. B, right here, this is emission, higher to lower. C is emission, also higher to lower. D is absorption, so I can get, because we're looking only for emission. And then E is also emission. So between B, C, and E, let's again, I put this diagram for you, or picture, so you can have a more visual way to process the information in the question. So 7 to 4, something here, like around here, so maybe 7 is very close to 5 and 6, okay, will be very close to 4. Okay, so 7 and 4 cannot be the smallest wavelength. Will be actually longer wavelength. So we're looking for the highest energy difference, and then between 4. So we have 4, and then 2 and 1. Of course, 4 right here is closer to 2 than is closer to 1. So the answer will be C. So emission, and then smallest wavelength, which is the highest energy. All right, now let's look at this practice problem. And as you see, I put the equation for you since you have it on your formula sheet. And another thing I want to mention, you're not responsible for reporting the amount of sig figs. The sig figs will be given to you on how many to report. And the question reads, what wavelength in nanometers of the line corresponds to the transition of n equals 5 to n equals 2. And so n equals 5 is going to be the final. And n equals 5 is going to be the initial. And n equals 2 is going to be the final. All right. And this wants us to calculate it in nanometers. Now, what we're calculating here really is the energy of the photon, okay? So this is here the energy of the photon. And first of all, I'm going to calculate the energy of the photon. And then from the energy of the photon, I'm going to use E photon equals to Planck's constant times the speed of light, h seat over lambda, which is the wavelength, to calculate the wavelength. And I know I didn't mention this here, but we're going to report the wavelength in nanometers. Okay, so let's start by the first step, and I can say that d delta E equals to negative 2.178 times 10 to the negative 18 joule times 1 over 2 squared, because this is the final, minus 1 over 5 squared. And this right here, when I plug it in my calculator, will give me negative 4.5738 times 10 to the negative 19th joules. All right. Now, if I want to calculate the energy of the photon, I will take its absolute value, right, which is 4.5738 times 10 to the negative 19 joules. And then the second step is I'm going to take this value right here and then plug it into hc over lambda. So I can say that I'll copy and paste this. All right, equals to Planck's constant, which is given to me on the formula sheet, joules times seconds, times the speed of light, also given to me on the formula sheet, divided by the wavelength in meters. And therefore, when I rearrange and solve, I get here 4.34166061 times 10 to the negative 7th meters. All right, and then I want to convert it to nanometers. So I'm going to multiply here by 10 to the 9th nanometers in 1 meter. And this is going to give me 434.316061 nanometers. I want to round now to 4 significant figures, so I can say that this is 434.3 nanometers.